supposed to lay by you. You just lay over there.
Let me be. Good morning. So are you ready for a quiz? I'm actually not personally, but well, yeah, don't make it sound like it's just a one-time thing. I was so ready the one time, and he didn't give it to me. All right, I'll give you guys a really piece. No, I'm not going. Not today, but I promise you they'll be coming. Let's see. But let's go over the basics and let's see how well practiced you are. Okay. Trigonometry, measuring triangles. What makes trigonometry possible? Right, similar triangles. Actually, tell me a little bit more. What about similar triangles is it that really makes trigonometry possible? Maybe you didn't quite catch this. Tori?
Like equal weight ratios?
Yeah, equal ratios, exactly. And isn't that, when you have similar triangles, what's one of the results from similar triangles? All the sides are, the corresponding sides are proportional, which is equal ratios, just like Tori said, and that's exactly what it is. Okay, now, let's review a couple other things. Actually, I've got the outline up here that we were looking at yesterday. We also learned what? That we could take these proportions that result from similar triangles and we could legally generate other proportions from them. And in fact, we learned 4 techniques for doing that. One of them was just kind of reading the thing upside down, called inversion. You could kind of read the old proportions sideways. That was called alternation. And you could do this numerator plus denominator over denominator equals numerator plus denominator over denominator, and that was called the addition method. You want to? It's okay. And then there was the subtraction method, almost exactly the same, huh? Numerator minus denominator over denominator equals same thing again. Okay, and then I showed you that if you combine those, you could generate new proportions literally forever. And every one of them, if you followed the technique correctly, would be legit. Okay. So it's time to move on now. Here's the portion. We're not going to do a real long portion today, and I started sneaking into this last time. Here's the portion of the outline we're going to do for today. And you'll notice I'm spilling the beans here a little bit early, but there will be a book assignment with today's work. So even though I'm not teaching out of the book, I'm kind of going side by side with the book. And when an assignment in the book would really be valuable for you to practice some of this stuff, I'm going to put it in there. And so I shouldn't do this ahead of time, but the assignment, besides studying, which is probably number 1, number 2, I want you to work on the odd problems 29 to 73 on a 6.1 assignment. If you want a page, that's starting on page 461. So the chapter in the book where we are kind of residing, even though I haven't shown you much in the book, is chapter 6. Okay, so do you remember I started showing you a little bit about how you can come up with this new type of angle measurement called a radian? And what was really unique, every other angle, isn't an angle just based on how far you rotate? You rotate this far, you got one angle, you rotate, really that's an angle. But this time, instead of how far you rotate, it's defined by the arc along that unit circle. And when that thing is 1 radius long along the curvature of the circle, then we have an angle of 1 radian. So an angle defined by a length is a totally different concept. And it's really important because this idea of linking to a length measurement, a circumference measurement, is really what makes radians so valuable. And just about our whole trig course is going to be based on radians. So I need you guys to adapt to that. In fact, today we're going to spend quite a bit of time on that. I suppose we should get into that right now. And then I'll come back. I see I have these slides kind of out of order. Okay, so first of all, a quick reminder from last time. Now I've got this triangle on there, but I just superimposed on top of it what a radian looks like. Remember, it's a radius laid out in 3 places. The bottom, where you begin on that positive x-axis, then somewhere up in the first quadrant there's another radius, and when the arc length that's cut off on the circle is 1 radius, then we call that angle 1 radian. Okay, review from last time. And then we started working our way around, didn't we? And so what I'm going to do is start working our way around. And to help me out a little bit, I superimposed a protractor on here just so that I could, I'll tell you what we're going to do. We're going to start with 30-degree angles. Okay, so what I'm going to do is just grab some lines here. I'll get rid of the protractor in a minute. And I want these, I want to go all the way to the other side of the circle. I want to go through the center. Okay, so there's a 30-degree angle. And then I want to do a 60. Okay, and then I want to do a 60-degree angle over here in the second quadrant. And I want to do a 30-degree angle over here. So basically what we've got here, yeah, I guess let me change colors, and with red, I'm going to also put in a 45-degree angle. And we'll do one over here too. Okay, now if I can pick it out of there. Yeah, now we'll get rid of our protractor. Okay, so the idea is all these black lines are 30-degree angles. And so let's just, I'm going to quickly erase this, but let me just show you. Remember, where's our initial side? It's down here, right? We'll always start on the positive x-axis. So here's my 30. Here's my 60. 45. Of course, we know what this is up here. This is 90. By the way, I'm only going to show these numbers briefly because we really need to get into radians. Then over here we have we're 30. Well, here's 180, and we're 30 degrees up, so this has got to be 150. This has got to be 135. And 90 plus 30, this has got to be 120. Down here, 180 plus 30, 180 plus 45, 180 plus 60. Down here we're at 270, here we're at 300, 315, 330, and you could call this both 0, and you could call it 360. Okay, now it's going to be clear, there's a reason why I only picked 3 angles in the first quadrant, 30, 45, and 60. And the reason is all because of geometry. I don't know if you remember this, but those three angles turn out to be pretty famously special, especially in right triangles. 45-degree angle is going to give you 45, 45, 90, an isosceles right triangle. And a 30-degree angle, I don't know if you remember this, it's probably a little, it seems like geometry trivia to you, but there's a pretty famous geometry theorem that goes like this. In a right triangle, the side opposite the 30-degree angle is 1/2 the hypotenuse. That theorem turns out to be very, very important in trigonometry. So anyway, we'll get to those famous triangles probably next time. So now I'm going to get rid of the numbers. And we're going to kind of do the same thing, only now we're really going to get to the heart of it. We want to do this all in radians. So like we talked about last time, what's the whole idea here is if 1 radian, and I haven't shown 1 radian on here, by the way, it's somewhere in, you need a radius about here. Something like 67 degrees, no, it's 57 degrees, it's right about in here. But, so I don't have a radian in here, but I do know this. How many radians are there if you go all the way around? Well, we know that circumference is, this is just a review, 2 times the pi times diameter, or 2 times pi times the radius. And if we divide that by a radian, remember, we found out that 1 circumference was 2 pi radians. So this is 0. We could also think of it as, instead of writing 360, now we're going to start getting our heads into gear in radians. That's 2 pi radians all the way around. So halfway around then ought to be half of 2 pi is, of course, 1 pi. And what's halfway between 0 and 1 pi? 1/2 a pi. And what's halfway between 1 pi and 2 pi? 1.5 pi. That's supposed to read 3 pi over 2 down there. I'll try that again. Pi looks kind of like somebody already ate it. There we go. 3 pi over 2. All right, now let's take a look at the first quadrant. We go from 0 to 1/2 a pi. And just looking at the black lines, don't we go in slices of thirds? In other words, 30, 60, 90. Those are nice equal pieces of 30 degrees. So if you take pi over 2 and divide it into 3 equal parts, each one is going to be pi over 6. So this 30-degree angle is pi over 6. And this guy over here is 2 pi over 6. Well, what is that simplified? 2 pi over 6 is pi over 3, right? And then isn't this just really 3 pi over 6? And what's 3 pi over 6 reduced? Pi over 2. Okay. So we just keep going in pi over 6. Let's do it again. Okay, now we have 1/2 a pi plus a 1/6. Let's see. Actually, I just thought of another thing we might do. I'm going to throw in a few more angles here. I just thought of another thing I could do to make this a little easier on you. So, let's see. Let me grab my protractor again if I can find it. And this time, I just want to throw some more 15 reds in here. So we'll grab some more reds. And we'll just run a 15. Actually, I should really do these dashed. Well, I went back to black. And I'm making these dashed because they really themselves don't make a very important part of this, but when you look at the whole piece, they give you then equal chunks all the way around, which can be used maybe to simplify the fractions. Okay, now let's get rid of that protractor. Okay, well, now, if 30 degrees is pi over 6, then what do you think 15 degrees is? What's half of pi over 6? Half of pi over 6? Wouldn't it be pi over 12? So here's what you could do. Think of yourself going around. Here's 1 pi over 12, 2 pi over 12, 3 pi over 12. What's 3 pi over 12 simplified? 4 pi over 12, 5 pi over 12, 6 pi over 12, which is pi over 2. We don't really care. 7 pi over 12. This one we do care about. 8 pi over 12. How could you simplify that? 8/12 pi. Two-thirds. Okay. So where was I? 6 pi over 12, 7 pi over 12, 8 pi over 12, 9 pi over 12, 10 pi over 12, 11 pi over 12, but I don't want that one. 12 pi over 12, pi. 13 pi over 12, dotted, I don't need it. 14 pi over 12. So what is that? 14 pi over 12. 7 pi over 6. 15 pi over 12. Is that right? 15 over 12 divided by 3. This should be 5 pi over 4. Sorry. Okay, 15 pi over 12. 16 pi over 12. 17 pi over 12. 18 pi over 12. 18 pi over 12. 6 divides into those and we get 3 pi over 2. 19 pi over 12. 20 pi over 12. Okay, 20 pi over 12. Divide everything by what? 4, and you get 5 pi over 3. Okay, I lost where I was. 18 pi over 12, 20 pi over 12, 21 pi over 12. 3 goes into 21 7 times, and into 12 it goes 4 times. So, okay, 21 pi over 12, 22 pi over 12. I better rewrite that. And, okay, that's 22 pi over 12, 23 pi over 12, 24 pi over 12 is just 2 pi. So, sometimes putting in those dashed lines, the 15-degree angles all the way around, give you these nice chunks of pi over 12. 1 pi over 12, 2 pi over 12, 3 pi over 12, and then you can just reduce your fractions. Anyway, you need to be able to navigate. I need you to start getting really used to this, okay? So if I gave you a circle, could you write these down? Did anybody have a question there? Where I got those from? Yeah, go ahead, Matt.
Is there maybe like a formula for converting degrees into?
Yeah, there is. I wouldn't want you to use it normally, but yes, there is. And let's just talk about that. In fact, you know what it is. Matt's question was, is there a formula for converting from degrees to radians and from radians to degrees? Yes. Okay, let's take one complete circle. What is it in degrees? What is it in radians? So we know we're starting here, right? So if we want to convert degrees into radians, let's divide both sides by 360. What do we get? 1 degree, I should probably put a degree mark over there. 1 degree equals pi over 180 radians. In effect, Matt, this is telling you, if you want to convert degrees to radians, multiply by pi over 180. Now let's do the opposite. Let's take that same equation, and this time, let's find out how much is in 1 radian. So this time we're going to divide both sides by 2 pi. So on this side we're going to get 1 radian, and on this side we're going to get 180 over pi degrees. And what this is telling you is if you want to change radians back into degrees, you could multiply by 180 over pi. Any way you look at it, though, to get good at this stuff, you do need to feel fairly comfortable with fractions, because you're forever working with these, you know, pi over 180, 180 over pi, 3 pi over 2. Fraction, you need to get a little bit comfortable with those fractions. Now, while I'm glad we went through this, and I guess it's important that you know you can do this, this is not going to be like the key emphasis, because I really want you to start thinking in terms of these angles that we outlined here. And by the way, I've got a nice, neat version of this. You notice this time I don't have those dashed lines in here. And this is up on the website, so you can print this out. You know, it's notes from class. So you can go get this if you'd like. But it's got the same numbers on we just did. All of them, it should be. Check to see if they're all the same. It's really a matter of, yeah, I got to tell you, one thing I don't like about the way this is written is this almost looks like 7 over 6 pi. And it's really saying 7 over 6 times pi. So the only thing I don't like about this graphic, you follow me? That does not mean 7 over 6 pi. So I guess the way I wrote it was a little bit better. Okay, well, we got to get used to this. And that's one of our tasks. At the same time, I don't want you to ignore the angle measurement. It's just that 90% of the time, when, in fact, I would say 98% of the time when you deal with trigonometry in calculus class, they are going to be talking radians. Radians is the language that you need to know in calculus. So I'm going to be pushing really hard that you get these radians down. And that'll be on your quizzes eventually and all that type of thing. In fact, eventually where we're headed is we're going to be making a chart. And one of the rows in the chart will be degrees, and right above it I'm going to have radians. And probably every one of these quizzes I'm going to have you guys translate from one to the other. I'd rather have you think in terms of the whole being 2 pi and fraction it out, but if you want to translate it, we just showed you how to do that too. Translate from one to the other. So, does this, I know this is a lot at once, but it's not that terribly hard either. It's just a matter of thinking in terms of fractions. And by the way, why did we wind up with pi over 12? Well, let me ask you this. How many slices did we divide the circle up into with these lines that are up there? Well, just take a look at 90 degree. Just in the first 90 degrees, how many chunks do we now have? 6, right? And that means altogether, all the way around the circle, we have 6 times 4, or 24. And what happens when you take 2 pi and divide it into 24 equal pieces? 2 pi over 24 is pi over 12. And that's why when we went around, we said 1 pi over 12, 2 pi over 12, 3 pi over 12. That, honestly, that might be the quickest way to generate this, if you just remember that pi over 12 thing. And then if you can simplify fractions, you can rip around and get this fairly quickly. Okay. Let me just get back to my roadmap. So we've pretty much done Roman numeral 3 now. Now Roman numeral 4. And we'll use this graphic for this. Okay? I have pictured here a right triangle. It should be obvious to you that our right angle is sitting down there in the corner. And what I want to do is name one of the acute angles. We'll name it angle theta. So theta refers to that acute angle down there in the bottom right corner. Okay? Now, a little bit from geometry. What do we call the two sides of a right triangle that form the right angle? I'll give you a hint. It's the body part. Legs, yeah. And what do we call that long thing? I'll give you a hint. It's a body part. Well, I call it a hip, but it's a HYP hip. Yeah, it's a hypotenuse. You're right. It's kind of a goofy way to look at things, because the poor soul that walks around with these two legs would have two legs of a different length, and that would be not so great. But anyway, in a way, you can think of it as two legs and a hip. Okay. This is called the leg adjacent. That means it's the leg that's adjacent to angle theta. It's the one that's next to it. You're familiar with the term adjacent? Next to? And this guy over here is called the leg opposite. Meaning it's the furthest leg away from angle theta. And then over here, like you guys said, okay? And now, the basic definitions of our trig functions. The sine, abbreviated SIN, is equal to the leg opposite divided by the hypotenuse. The cosine, abbreviated COS, is the leg adjacent. Divided by the hypotenuse. The tangent abbreviated TAN is the leg opposite divided by the leg adjacent. Okay, if you haven't already, those simply must be committed to memory. You've got to have those babies nailed. And I mean, we're going to be hammering that to death. You've really got to know that. Now, I don't know if you're into acronyms, but you probably all know this. Looks like, I don't know, an Indian word or something, SOHCAHTOA. But if you think of this, this kind of says the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, the tangent is the opposite over the adjacent. Okay, the problem with little memory aids like that, I'll never forget a student I had who remembered SOHCAHTOA beautifully, got his entire quiz wrong. Reason? He spelled SOHCAHTOA wrong. So here's the here's the problem with memory aids. If you make a little twist in the memory aid, you can get completely discombobulated. Okay. I don't know. Another one I remember from. I still remember it from it was like the first day of high school, and that was Roy G. Biv. You guys remember Roy G. Biv? You know what I'm talking about. Yeah. I don't know. There's certain ones that stick. Hopefully this one will, but if you don't want to use that, fine. Just got to find a way to remember it, okay? Okay, so I believe if I look at my roadmap, yeah, the outline tells you that we defined, by the way, there are 6 trig functions, not 3. But you'll notice I haven't given you the other 3 yet. That's because the other 3 are just kind of a manipulation of these 3. And so for the time being, we're going to do without them. Okay? They're called the reciprocal functions. We'll get to them. Okay, let's see what the assignment has entailed for us. So if you have your books handy, open them up to page 462. Okay, now, yeah, maybe before we talk about the written, I just want to emphasize your top priority for tomorrow. Study. Don't forget about the stuff we talked about last time. What's the foundation for trigonometry? What makes it possible? Good old similar triangles and those proportions. How do I rewrite proportions legally? And now today, how do we define the sine? How do we define the cosine? How do we define the tangent? Those have to be. How do I divide this circle up into radians? There's a fair number of things you got to get up into this space, okay? And you got to do that by tomorrow, okay? That's your top priority. This is going to kind of help it along, though. This isn't really hard stuff. If you look at, what did I tell you, 29? I guess I gave you the wrong page. It's 461. Number 29 says, can you tell me which oh yeah, I didn't talk about quadrants. I'm assuming everybody knows how the quadrants are numbered. I mean, that's an assumption I can be able to make, right? Where do we begin? 1 is up there, 2, 3 down left, 4 down here, right? Okay, so in number 29 they're saying, here's an angle, pi over 5, and of course all of these, anything with pi in it, you can right away immediately assume they mean that this is pi over 5 radians. All right, which quadrant is pi over 5 radians in? Now, they're trying to get you to think in terms of radians. Remember, from here to here is the first quadrant, and we know this is 0 and this is pi over 2. So if this is half pi, then where's a fifth of pi? It's got to be in here, doesn't it? And therefore, doesn't that have to be a quadrant 1 angle? So you see what they're doing. They're trying to get you to think in terms of pi radians. Next section, 35 to 38. Sketch each angle in standard position. What's standard position? Standard position means the first side of your angle will be along that positive x-axis that I've been, where 0 is. So if you were going to sketch, we don't want you to do any protractor stuff, okay? But where is 5 pi over 4? Well, where's pi? Out that, it's 180 degrees, right? So wouldn't 5 pi over 4 be past that? And it's past it, pi over 4. What's pi over 4? Isn't that a 45-degree angle? So in effect, what they're telling you is, your angle, draw one side here, and then your next side is going to be down at a 45-degree angle. So that's an obtuse angle, right? So you're going to, you're going to draw something like this. Got your first side, and then your second side. And, it wouldn't hurt to draw that little arrow in, because otherwise some people might think you're drawing this other angle here. You follow? And somebody could look at this and go, oh no, your angle's too small. You should have, so maybe just sketch that in there too. I mean, we're not going to pull a protractor out and see, are you off by a degree? No, we want to see that you got middle of the third quadrant. Okay, what's the next section? Starting at number 39, it says, determine two, okay, here's a term I need to explain to you. It says, determine two coterminal angles, one positive and one negative for each angle. Okay, here's a term I haven't told you. Coterminal angles are angles that begin and end at the same place. Okay? So, a 30-degree angle, you know what that looks like. 30-degree angle looks something like this, right? Approximately. Okay. What other angle has its same beginning here and its same ending here? Couldn't you go around this way? And since you're going around the opposite direction, that would be a negative 330. Yes? Okay, now, who can come up with another one? What's another angle that begins here and ends here? A third one. Well, it's not hard. You could just go, you know what I mean? Make a complete revolution and then stop up here. So that would be just 360 plus 30, or 390. And then, isn't another one? Two revolutions, and there's a ton of those. Any angle then that has the same beginning and the same ending point, same initial side and the same terminal side, are called coterminal angles. So now that part shouldn't be that terribly hard after I told you that. 43 through the next section says, find, if possible, the complement and the supplement of each angle. Okay, now you know a complement means what? Together they have to form pi over 2, radians. Supplementary, together they form pi. Okay, so, 43a, I guess they're checking if you know how to subtract. Now it gets a little bit tougher when you get to like 47. Okay, what's the complement of pi over 12? Well, what does pi over 12 have to, what does this other angle have to add up to for complement? It's got to add up to pi over 2. So, you could just think like this. you know, what do I have to add to pi over 12 to come up with a full pi over 2? And really, then, isn't this... And then really all you need is a common denominator, isn't it? When you do this, isn't this the same as this? And what's 6 pi over 12 minus 1 pi over 12? 5 pi over 12. And there's your complement. Okay, so you get, again, you're going to get a little practice dealing with fractions, actually more than a little. There's going to be a lot of fraction thinking, but not difficult fractions. So what are you going to do in 51? It says express each of these in radian measure as a multiple of pi. Well, all of those come right from our chart, don't they? What 30 degrees is what fraction of pi? Pi over 6. And so isn't 150 degrees just 5 times that? Because isn't 150 5 times 30? Well, if 30 degrees is pi over 6, then shouldn't 150 degrees be 5 pi over 6? And you can do easy things like that. So it's kind of handy to know 30 degrees is pi over 6. And then you can figure out a lot of cool things. What's 45 degrees? Pi over 4. You get used to those basic ones in the first quadrant, and you can maneuver pretty nicely. What else could you do? If you couldn't remember that, you could use the formulas that Matt asked me to show. That's not my preference. I think you're better off thinking in fractions, but you could take the formula, multiply it by pi over 180, simplify your big old honking fractions that you're going to have, and you got it. You can do it that way too. That's not, I don't think that's the ideal way to do it, but you could. Okay, how far did I have you go? 73? So the next section is change to radians. Now here you don't have much choice. They gave you some decimals, so what are you going to do? You're going to multiply by pi over 180. Use a calculator. So on your calculator, if I'm going to do number 61, I'm going to plug in negative 216.35. I am going to say times, and I'm going to hit my pi t, and then I'm going to just divide by 180 equals. Now, well, I take that back. They want the answer. Yeah, they want it in decimal radians. So that would be how you do that. 67 to 74. Can you convert these back into degrees? How do you convert to degrees? Multiply by 180 over pi. You know, just think of it this way, by the way. That's pretty easy conversion. How do you remember that to change to radians, you have to multiply by pi over 180? Simple. Radians almost always have pi in them, don't they? So just multiply by the thing with pi on the top. Degrees never have pi in them. So what do? You multiply with a pi on the bottom so the pi's cancel. Pretty easy to remember. Okay, so I gave you a bunch. We got a whole bunch of stuff to go into this big, wonderful book, projector, computer processor up here. And then you have some written work to do. See you tomorrow. Take care.